Hello, welcome to lecture 4. In the earlier lecture, we derived the Reynolds transport theorem. In this, we will see how the Reynolds transport theorem can be used to derive the conservation of mass and conservation of momentum. So these are very crucial equations of fluid mechanics applicable for all fluids, like whether it's liquid or gas, and we'll derive the general form because these forms will dictate the form of all the flows that we'll be studying as we go along in this course. So let's start with the conservation of mass from Reynolds transport theorem. So in the Reynolds transport theorem, I'll write down the statement, the mathematical form of the Reynolds transport theorem again. dB system by dt is equal to the integral of the control volume over the control volume, the partial derivative of this quantity b rho, plus integral over the control surface v rho u dot n cap dA. dA is an infinitesimal element in the control surface, d lambda is an infinitesimal volume in the control volume, and capital B is the extensive quantity, small b is the intensive quantity, rho is the density here, u is the velocity by which the system is moving out of the control volume. So now once we have this form, so for conservation of mass, set small b equal to 1, the intensive property to be equal to 1. Hence, so the capital B would be the mass variable m. Okay, so for a control mass system, that is fixed mass and identity. So these same elements of fluid, we are considering the same elements of fluid, so they are not changing, they are not intermixing, and the mass of course remains fixed of a system. So this is a control mass system, so the mass is not varying. Hence dm system by dt is equal to 0, and this is equal to cv d rho, the partial derivative of rho del rho by del t, or d lambda, that is over the control volume, and then integral of the control over the control surface of this quantity u dot n cap dA. This is just the statement of the Reynolds mathematical form, the Reynolds transport theorem. We have just substituted small b to be equal to 1. Now this can be, I'm just changing the right hand side to the left hand side. So the student can pause here themselves and think why this has happened, why have I introduced this term. So there is a theorem by which I have done this, and you can pause it and guess it yourself, but if you have not guessed it, the name of this theorem is the Gauss divergence theorem. So I applied Gauss divergence theorem. So the integral of a quantity over a control surface is equal to divergence of the same quantity over the volume which is bounded by the control surface. Okay, sorry, this is control volume. This is control volume, and divergence of this quantity rho u vector over the control volume. So after this, so we can because now we have both the integrals over the control volume. We can club both of these integrals, both of these quantities. So this is integral over the control volume del rho del t plus the divergence of this quantity rho u, and integral over the control, integral over the whole control volume. Now this, given that this whole integral is 0 and given that this holds for any arbitrary CV, since the control volume is arbitrary, the only way this is 0, this equation holds, is that the integrand is 0. The integrand is 0. That is, now we have del rho by del t del dot rho u equal to 0. So this is the conservation of mass or the continuity equation. We have easily derived it from the Reynolds transport theorem by substituting the intensive property to be 1 without any loss of generality, and this is the this is the form of the conservation of mass. So this can we can also expand this to write it in a different form, because now we know what the total derivative is. We can also expand this, and this is just a one line algebra that you are expected to do yourself, that we can write it in this form. Now again, the students should remind themselves what is capital D dt. So the capital D dt is the total derivative. So this is the derivative following a partial when it's a derivative which includes both the temporal rate of change of something, and then of a quantity, and the advective rate of change of that quantity. So the reason why I could do this, because I expanded the second term, and this is left as an exercise for you to, it's just one step to get to this form. So once we have this one, there are just some statements. So fluid is called incompressible if the density remains constant with change in pressure. So for an incompressible fluid, the change in the density is 0. So this is the definition of an incompressible fluid. So the continuity or the mass conservation equation hence the continuity equation takes the form the divergence of u is equal to 0, because this first term is equal to 0 in an incompressible fluid. The density following the motion of a fluid element remains constant. Hence, for an incompressible fluid, the mass conservation equation takes this form. So there is something that we can infer also from here, that the conservation of mass for an incompressible fluid puts a restriction on the way or restriction on what velocity fields can appear in the system. Okay, so this as you can see, this means that the divergence of the velocity is 0. That is, there cannot be arbitrary sources or sinks in the fluid, and this comes from the fact that the fluid itself should conserve mass. So for an incompressible fluid, this limitation has been set by the property of the fluid itself. Okay, so the property of the fluid is now putting a restriction on the quality, or at least the or the velocity field that is admissible in the fluid. So incompressible flows cannot have any arbitrary velocity fields. This should satisfy that the divergence of the velocity field should be zero. This is what the conservation of mass for an incompressible fluid tells us. Now, once you have derived the conservation of mass, the obvious extension is the conservation of momentum. The conservation of momentum is, in simple terms, is that if there are no external forces acting on a system, the total momentum of the system will be conserved. So in this conservation of momentum, again we'll use the Reynolds transport theorem. So in this, let the intensive property B is equal to the velocity. Okay, so we can put the intensive property to be anything. We are not bound by any physical law or constraint which puts a restriction on what we can choose B to be, but so we choose B to be U. So capital B is equal to U times M. So this is the, as the reader might, the student might have already guessed, this is the linear, already found out, this is the linear momentum. So capital B is the linear momentum of the system, and as you can see, this is an extensive property. This depends on the mass of the system. Okay, so if a body of 1 kg moving with 1 meters per second will have momentum 1, whereas a body of 10 kgs moving with 1 meters per second will have momentum 1 kg meters per second. 10 kg meters per second. So that is 10 times higher. So the capital B is not dependent on the mass. Hence, this is an extensive property. So now once we have this, so we have ddt of the system. So this is what we get from the Reynolds transport theorem, is equal to the rate of, change of the velocity integrated over the control volume, and then this is the control surface, integral over the control surface of this term U dot n cap. So actually this should be, this M can be written as rho d lambda, so that we do an integral over the control volume. Okay, so d lambda is the infinitesimal volume. So this makes it mathematically sound now, rather than putting it as dm. So from this we write, so this is just replacing small b in the Reynolds transport theorem. We now have so we've written down the left hand side as the rate of change of the linear momentum. So P is the linear momentum. So you can obviously write this form. So in an inertial frame of reference, this the rate of change of this linear momentum, as I said, will be equal to the sum of the external forces acting on the system. So this is nothing but the Newton's second law of motion. So the linear momentum has to be conserved if external forces are zero, but however, linear momentum can change if there are external forces acting on the system. So this is for an inertial frame. So we will come back to frames of reference in the next few lectures, where we discuss non-inertial frames of references. But for now, let us consider only inertial frame of reference. Non-inertial frames comes because the Earth is rotating, and as I mentioned in the previous and in previous lectures, and also in the first lecture, that the flows of the motion that we'll be studying are affected by rotation of the Earth. So we have to keep so we are just building our base now to get to the non-inertial frames of reference. We are getting the momentum first. We are getting the conservation of momentum in an inertial frame of reference, and then we will see how the non-inertial frame, that is a rotating frame of reference, changes the conservation of momentum, because all these laws are valid for inertial frames of references. So using this, we can write, just clubbing the terms together, just verify yourself from the last slide that we can write it in this form. So I have introduced this new notation. So this is the tensor product. So this comes from the this term u dot n cap. So these are two vectors, and we have some basic knowledge of vector algebra. So the divergence operator reduces the rank of a tensor by 1. So this is a tensor product, and this gives rise to a second order tensor. And when the divergence operator acts on the system, acts on this product, it brings it down to a vector. This whole term has to be a vector because this term is a vector. Okay, so we can only add terms which are of the same order. So it's a this u vector is a first order tensor. This is a second order tensor, whereas divergence operator is acting on this, and it's reducing its rank by 1. Its order by 1. So u tensor is, so this is the tensor product. So this is the tensor product, and this is equal to ui uj. So this is a matrix. Okay, so ui uj. So I've written this in Einstein notation. I would encourage, if you're having some difficulty understanding the notation, to revise the Einstein notation. So how the subscripts are written, what are contraction of subscripts, how multiplications are written in Einstein notation, so that it becomes easier for you to follow. So this one, moving ahead now, so this is equal to the external forces, some of the external forces. So this is the integral form of the momentum equation. We'll derive other forms also, so the differential form also. So this is the integral form of the momentum equation. This is the integral form of the momentum equation. So now, what are the kinds of forces that can act on a system? So that will help us break down this equation into slightly more in terms of variables that we usually encounter. For example, let's say gravitational force or other kinds of forces. So the external forces can be that can act on a system. Simple forces that can act on a system. Simple forces that can act on a system, these are body forces. So the body forces are gravitational force, gravitational attraction, gravitational force. There's something that acts on the system, and it does work as if the whole system is one body. And this works. I mean, the forces acts on the whole volume of the system. And the other kind of force is surface force. Surface forces, these are forces that act on the surface of a system. So these are examples are pressure and viscous forces. Examples of simple forces. We are keeping our system simple. So for an arbitrary system, so for an arbitrary surface, the force on the surface can be represented as the integral of the stresses that are acting on the control surface. So this tau with this double bar is a stress. So this is the stress tensor. So this has these elements. So this is the stress tensor, and this gives us information regarding the direction of the force and the direction of the surface on which it is acting. So and n cap is the unit vector where n1, n2, n3 are the three orthogonal directions. So we are always working on 3D Cartesian systems. So now we can write the from the previous slide, from the integral from the momentum equation. So we can write this as, so integral over the control volume of this quantity. This has come from the previous equation. It is I'm just writing down the left hand side, is equal to the sum of the external forces. Now in previously we had just written this as sum of the external forces in the top right corner here. Now we are expanding this force in terms of something that we understand, for example gravitational force or other kinds of surface forces. So now this is control surface tau dot n cap dA, and this can be, again I'll just write down this term only, again represented as a divergence of the stress, but the integral over now the control volume. So again the student might pause and they can guess what has been applied. This is the Gauss divergence theorem. I have applied this previously also, and I have applied it again. So I'm because I want to have now an integral in the control volume, so that I can club both of these together, both of these terms on the right hand side together. So now clubbing all the terms together, we get this whole integral is 0. Now again, as this whole for any arbitrary control volume in the system, so this integrand should go to 0. Okay, so this integrand is rather 0 for this equation to be valid. So this gives us so this is a form of the momentum equation. So this is called the conservative form of the momentum equation. And so the other one was the integral form. This is the differential form. So this is the conservative form of the momentum equation, and the conservative form is a specific variant of the differential form of the momentum equation that we have been discussing. You can also write the non-conservative form of this differential equation. So in index notation, Einstein notation is something that you can read in the background, study in the background if you have forgotten, and this is how we can express the momentum equation in index notation. So now here, as you can see, we have a quantity which is unknown to us. So this is a quantity again which is unknown, and we would like to expand this so that we express again this in terms of some of the things, some of the variables that we know. So this tau ij is unknown, so we need to find a relationship between the stress and the rate of deformation. So we need a relationship between tau and rate of deformation. So rate of deformation of the fluid element of the system. So and this relationship is called a constitutive relation. So again, now we have done this in advanced fluid mechanics courses. So tau ij can be expressed, I mean, it can be decomposed into hydrostatic and the deviatory component. So then we'll find out the constitutive relationship for a Newtonian fluid. So tau ij, however, I mean, generically can always be divided into hydrostatic part and the deviatory part. And the hydrostatic part exists even when there is no fluid motion, whereas the deviatory part exists when there is a fluid motion. So there is always something which is pushing a fluid element from all the sides. This is the hydrostatic stress. But when it starts moving, there are surface forces that are generated on the surface, through the surface, on the fluid element, on the fluid particle, and this is the component, this is the stress given by the deviatoric part. So this deviatoric part has a form lambda So these are this is the form of the deviatoric part of the stress tensor, and this is called the second coefficient of viscosity. This is called the second coefficient of viscosity. So this is the rate of volumetric deformation rate of volumetric deformation. This is plainly called the viscosity of the fluid, and this is the rate of shear deformation. This term is called the now why the first term is called volumetric deformation is because you have UK and XK, the same indices. So this quantifies the fractional change in the volume of a fluid element per unit time due to motion, and this term also represents the divergence of U, whereas this last term gives a measure of the shear deformation. So this is the form of the this is the form of the deviatoric part of the stress tensor. Now hydrostatic part, so this hydrostatic stress is isotropic, so it must be of form it must be of this form because it's a second order tensor, and delta ij is the only second order isotropic tensor. So this is the and this quantity P is the thermodynamic pressure. So this is for both fluids and so it exists for both fluids in rest and in motion. And the negative sign is because pressure is compressive by definition. Pressure is compressive and tensile forces are regarded as positive. So this is compressive force.